So in the last lecture, we discussed about entropy and we defined what is entropy, and we also showed how entropy changes happen for different processes. And we showed that in general, for any the irreversible process, the entropy change of the system must be greater than 0, and the entropy change for the system and surrounding together, or the entropy change of the universe, also must be greater than 0. Now natural processes are irreversible process. For example, let us just take the example of, say, growth of any animal or tree. So we get born and then we get old and then we die. So that's an irreversible process. There is an arrow of time associated with it. An old man never gets younger with time. So there is a concept of directionality or time, arrow of time of any irreversible process. Now we are going to consider this directionality, and for any reversible process the system can actually go back to its original state. So we are going to consider first what are the conditions for spontaneity of a process and what are the conditions for the processes at equilibrium. By processes at equilibrium, we mean that it's a reversible process, because at equilibrium we know that reversibility has to be maintained. That is the meaning of equilibrium. And by spontaneity of the process, we mean that the process has to be irreversible. There is a directionality, that it goes from say in a particular direction. For example, we know that water flows from high altitude to low altitude because of gravity, or heat flows from a hot body to cold body because of differences in temperature. Those are all spontaneous processes. And if for an equilibrium system, we are also going to discuss what are the conditions. So the first thing first, we can argue from our previous discussion is that we can relate everything to the changes in entropy of the system, which means that we already discussed that the heat change for any reversible process associated with the surrounding will be heat change associated with the system. So the ds universe, which is the d cross q surrounding divided by temperature of the surrounding plus d cross q system divided by the temperature of the system, which has to be greater than equal to 0. If it is 0, we know that it's a reversible process, and it will be 0 only when you can see here that if I make it 0, the condition is T surrounding must be equal to T system, which means it is also isothermal. Now for any irreversible process, which are naturally adiabat, so we have a condition that ds universe is greater than 0, and we can easily argue that this ds universe is nothing but this part is coming from ds of surrounding and this part is coming from the ds of the system. But for any process, the ds of the system, then if this condition has to be valid, ds of the system can be equal to d cross q reversible. It is defined as d cross q reversible by t, but which can be equivalent to the d cross q system of divided by t if the process is reversible, because this is the definition, remember. However, it is not always true that these only for reversible changes the heat changes are equal, but for irreversible change we know that the ds of the system must be greater than equal to the ds of the surrounding. This follows, let us just use this equation first. We can easily then understand how we arrive at the condition for spontaneity. So we just discussed that ds universe, which is nothing but ds system plus ds surrounding, is greater than equal to 0, which follows that ds system must be greater than equal to minus ds surrounding. But we know that ds surrounding is nothing but d cross q surrounding by t, which is minus d cross q surrounding by t. And then we also know that there should be a negative sign here because the heat withdrawn from the surrounding is heat gained in the surrounding. So which is greater than equal to d cross q system divided by t. So from here we can just rewrite the condition for spontaneity is that we have or we can write it just like we discussed. ds of the system is greater than equal to d cross q system divided by t. Now this holds for any reversible as well as irreversible process. This is not only the reversible process, this heat change, because that by from first law we know that the heat changes must be equal. So we get a very interesting relationship. So the equality, if it is equal, it is a greater than equal to, you can see it will be a reversible process. If it is greater than, it will be an irreversible process. So these two are the conditions for spontaneity and equilibrium. So what we just showed is that the entropy of the system, which is defined as the reversible heat change at constant temperature, which again can be equated to the heat change associated with the process, but that heat change may be identical to the reversible heat change if the path is reversible, which means the process is an reversible process. However, if the path is irreversible, then the associated heat change will always be less than the reversible heat change, and then you can show that the ds system will always be greater than or equal to d cross q system by t. Now we'll use this condition to understand what are the conditions for spontaneity and what are the conditions for equilibrium. Now we can right away use the first law of thermodynamics to get a relation between this condition of spontaneity and equilibrium and the internal energy. Now for that we just write du from the first law is nothing but d cross q minus p opposing into dv. Now all we have to do is to get the equation for the entropy. Now you can see that since dq is nothing but if the process is reversible, instead of dq we can write as tds, or where actually tds is nothing but the entropy of the, so this is we could have written it as tds is greater than equal to d cross q, and we are dropping the notation sys or system because it is obvious that we are only dealing with the system's notation. So we could write that since tds is greater than equal to dq, so this dq, so this du will be less than equal to tds minus p opposing into dv. Or we could write that if we just rearrange this term, that minus du minus p opposing into dv plus tds that is greater than equal to 0. So this is the condition for spontaneity and equilibrium together. If it is 0, it is spontaneous. If it is greater than 0, it is if it is 0, it is at equilibrium, and if it is greater than 0, it is a spontaneous process. Now the question is, of course we got a relationship for the spontaneity and equilibrium. Now we'll move on and discuss the conditions for equilibrium. We just said that we can write the first law. Instead of writing as du is d cross q, we write it as TdS, and this equality sign holds only for equilibrium, remember, minus P opposing into dV. So this is and if it is an equilibrium, also remember that the opposing pressure will be nothing but equal to the pressure of the system, because equilibrium means reversibility is maintained. So du is TdS minus PdV, and that will be our first equation to start with. Now we will use the other definitions of, say for example, enthalpy, and we'll also define some new energy terms today, and then we'll see how the differential relations look like. So we know that H is U plus PV, so we can write dH is equal to du plus, just following the chain rule, PdV plus VdP, and then for du we can write TdS minus PdV, this is the value of du, plus PdV plus VdP, and then this PdV cancels, then we get dH is nothing but TdS plus VdP. So similarly, we can define two new quantities. We call it as A, which is U minus Ts, just like we defined H as U plus PV, and this A is called Helmholtz energy, or sometimes called Helmholtz free energy. And similarly, another quantity which we'll call as G, which is nothing but H minus Ts, and is known as Gibbs free energy. So this if we use these two relations and just try to understand what is the differential for dA, it's again will be a chain rule. For example, dA will be du minus TdS minus SDT, and we can easily show that it is nothing but minus SDT minus PdV, and similarly dG is nothing but minus SDT plus VdP. Now we have four equations. One is for du, which is TdS minus PdV. One is for dH, which is TdS plus VdP. One is for dA, which is SDT minus PdV. And the fourth one is for dG, which is minus SDT plus VdP. Now we'll move on and see how one can use these relations very cleverly to build many differential relationships between different thermodynamic quantities. Now what we mean by that is, suppose we have some function z, which suppose we can write it as a function of x and y. So the total derivative we discussed is earlier can be written as a partial derivative with respect to x, keeping the y constant, plus partial derivative with respect to y, keeping x constant, and we can write it suppose as my dx plus, or we just write it as m, we drop the notation y plus n dy. So m is nothing but the partial derivative with respect to z, and n is nothing but the partial derivative with respect to x, and n is nothing but the partial derivative with respect to y. Then if we further take the differential of z, we know that due to the reciprocity relation, we can write that the order of the differentiation does not matter. This is known as the Euler's reciprocity relation, and due to this reciprocity relation, we can write that del m, because del z del x was nothing but m, del m del y is nothing but del n del x. So let us now use this, or use this Euler's reciprocity relation to this is actually known as Euler reciprocity relation, and which comes from the notion that the order of differentiation doesn't matter. So we can now use the relation, say, for du, which was TdS minus PdV. Now we can actually make a connection that here u is, here our z is nothing but u, and t is, just follow this equation, t is nothing but m, and p is nothing but n. So it is associated with ds, you can see m dx. So x is nothing but x, and v is nothing but y. I was using small x and small y, so I'll just use that same notation. So we can now use this reciprocity relation, which is del m del y will be del n del x, and that right away tells us that del s, you can just follow from here, we have del m del y, m is t, so it is del m, it is del t, and del y, y is v, del t del v will be equal to, and when we did this differentiation, we kept x constant, so it is at constant entropy, which is equal to n. N is nothing but p here, but in this case it's not p, it should be minus p because there is a minus sign. It will be del of minus p with respect to x. X is nothing but s when we kept the v constant, or we can just rearrange a little bit, which is del t del v s is nothing but minus del p del s. So these kind of relations are basically writing, helps us to write formulate a differential relation between various thermodynamic quantities, and these differential relations are known as Maxwell relations. Now we have just used only one equation, which is du equal to TdS minus PdV. We could use, or we could apply the same chain rule process for other differentiation to get other Maxwell relations. Let us just calculate one more. We already discussed that the equation for dH will be nothing but dH was TdS plus VdP. So in this case, an easy way to remember is that we'll take the partial derivative again with respect to P and with respect to S. So if we take the partial derivative with respect to say S, because the differentials are here ds and dp, so what we will get is del t and then del p. We are taking this quantity's partial derivative with respect to this differential del p, keeping s constant, will be equal to del v. Now this quantity, taking the partial derivative with respect to s, del s, keeping p constant. Similarly, we'll have del s del v t, which will be which we can use for the third relation, which was basically dA is minus s dt minus p dv. That will give us a relation for this. We are coming back how to get the relation, and from the equation of dg we can equivalently, dg was minus s dt plus v dp, we can equivalently get a relation for del s del p t. Now from the first relation, which was du equal to tds minus pdv, we already showed that del t del v s is nothing but minus del p del s v. Now how do you judge that what are the relations? How do you remember it? Now look at it, that I'm asking, suppose what is del v, del t del v s, or partial derivative of temperature keeping the entropy constant. Now what are our energy terms? We know that PV is an energy term because it's a pressure volume work is equivalent to energy. Similarly, ST is also an energy term, because if you remember, we wrote that du is TDS or dH is TDS. So ST must have a dimension of energy, and you already know that S is the dimension of heat divided by temperature, multiplied by temperature will be dimension of heat, which is a form of energy. So just keep that in mind, how the energy terms are coming. So here, look at here, like I have ST here, and then on the right hand side I'll just use to memorize it, I'll just use this mnemonic to keep that in mind, that I have del t here, I have del s here, so these are ST are energy term. So if I have V here, I should have P here. That is one thing. And then I'm keeping ST, so that's the energy term, so I have to keep the V here as constant. Let us take the second example. Here I have T and S, which are energy terms, and here I should then have a V here, P and V, and then TS, so then VP. Only thing you have to keep in mind, wherever I have a del P, either in the numerator or denominator, I'll have a negative sign. So the way to remember is something like this. I have a relation like this, and then if it is S here, it will be T here, or if it is P, it will be V here, something like that. Similarly, I'll just look for the energy terms, and also this constant term here will have a relation with this term, keeping in mind that I'll have only PV term, PV like term or ST like term. And the second thing is that anything, if del P is there, should be negative. Now let us, using this rule or using this just trick, try to get what we should get for the del S del Vt. Now since it is del S, so it should be del T here. Since it is del V, it should be del P here. And since it is T, where St is the energy term, I should have V here. Similarly, here it is del S, so I'll have del T here. It is del P, I'll have del V here, and then it is St, I'll have P here, PV. But since it is a derivative with respect to pressure, I'll have a negative sign. So this is an easy way to memorize all these relations, which are in general known as Maxwell's relation. So we have four Maxwell's relation. One is the first one, del T del V S is del P del S V. Then the second one, del T del P S is del V del S P, and so on. So I have basically four Maxwell's relation. Now we are going to use this Maxwell's relation to figure out how we can write some other relations from these very interesting relations which are known as Maxwell's relations. Now let us first write the first equation, which is du is TdS minus PdV. Again, remember that we are using the equal sign, keeping in mind that equality means the system is at equilibrium. If it is spontaneous, we have to write it that fundamental condition that minus du minus PdV plus TdS must be greater than 0. We are only considering systems at equilibrium, not for any spontaneous process. So that's why we are using the equality sign. Now we already said, let us just take a derivative with respect to volume. If we do that, we can get a equation for pressure. So which means if we take the derivative with respect to volume, keeping the temperature constant, we have to keep the temperature constant, because unless we keep the temperature constant, if we take the volume derivative, then I'll have two terms here. One will be derivative with respect to volume, and then again derivative with respect to temperature. That's what we are not doing. So we'll have the temperature constant and del S del V T. Remember, it's a differential with respect to volume. And then I have minus P. So we get a very interesting relation which basically tells us how the pressure can be expressed. So it is nothing but T del S del V T minus del U del V T. Now we can now use Maxwell relation to instead of writing it in terms of entropy, we can write it the other way. It is del S, remember, so I'll have a del T here, and it is del V here in the numerator, so I'll have a del P here, and since it was T ST combination, so I'll have a BV combination minus del U del V T. So that's a new expression for pressure, and these equations are known as thermodynamic equations of state. So we are actually not writing this PV equal to nRT, or the ideal gas equation, or something like a van der Waals gas equation which we discussed, but this is independent of the system, and we wrote the pressure as in terms of partial derivatives of pressure, temperature, volume, internal energy, and some other quantities which we can measure. So this is a new way of writing the equation of state for any arbitrary system. We can actually apply it to ideal gas, we can also apply it for real gases. Now let us see if we had proceeded with the other equation for dH, which is TdS plus VdP. So as before, if we take a derivative with respect to pressure, I will get an expression for volume. So let us calculate it. Del H del P keeping the temperature constant. So I will have T del S del P T plus V. So volume is nothing but, what we get here is minus T del S del P T plus del H del P T. Now again we can use Maxwell's relation, minus T into del S. So we'll have del T here because it's a ST term, and we had dP in del P in the denominator, so we should have del V here, and since it has ST, it will have PV combination, plus I have del H del P T. So this is another thermodynamic equation of state that we just discussed. Now we know that del U del T for ideal gas should be equal to 0. We can actually quickly check. We can use the PV equal to nRT relation here. So if we use it, what we get is del U del T. So this quantity we are measuring is nothing but T into, basically we are using this equation or the second equation, T into del P del T V minus P. Now what is T into del P del T V? So we have to write pressure in terms of temperature, which will be nRT divided by V. So if I take the derivative of nRT divided by V, keeping the volume constant, it will be nothing but nR divided by V minus P. So that is nothing but P minus P, which is 0. So which we already know that del U del T is 0 for any ideal gas. So this equation or this equation is a general equation. Similarly, you can also test for ideal gas. You will find that del H del T is 0. And remember, these two are some interesting quantities which we discussed, that del U del T was 0 for ideal gas, and it was measured by Joule in Joule's experiment. Although later on people found that actually it is non-zero, because if you are doing an experiment, of course you are working with real gases. For ideal gas it is 0, but for real gas it will be non-zero. And if you do enough refined experiment where the sensitivity of the experiment is good enough that you can detect the change, then you will find that del U del T will be non-zero. Similarly, the del H del T, remember, was measured in Joule-Thomson effect and Joule-Thomson experiment, and where they found that del H del T can be connected to the drop in temperature with respect to pressure, and that they termed as Joule-Thomson coefficient, and from that you can calculate the del H del T. Now we will proceed on this discussion, and where based on the discussion, where we'll be using this relationship of pressure and volume, or the thermodynamic relations, and then we will use it to calculate other thermodynamic quantities, something like say Cp minus Cv. Now Cp minus Cv we already discussed for ideal gas, but what happens for, say, for example, if you ask this question, what is Cp minus Cv for a solid, then we cannot use an ideal gas equation to begin with, and then we have to use a general equation. For that we will use similar relationships, because all these fundamental relations like du equal to TdS minus PdV or dH equal to TdS plus VdP, these are just fundamental equations. We do not make any approximation or any assumption here. All we said that these are fundamental relations coming from the concept of entropy and the concept of spontaneity and equilibrium. We are only considering the equilibrium process because it's an equation of state, and equation of state means it will only describe the properties of the state. These equations will describe the properties of the state, which means the system must be in equilibrium, thermal equilibrium as well as material equilibrium, and then the equality sign holds. Otherwise, there will be a greater than or less than sign, which we can always derive from the fundamental condition which we just discussed, that du minus pdv plus tds will be greater than equal to 0. Now suppose we are dealing with a piece of metal which is a solid, and for that solid or gas we can actually define some other quantities, say for which we can measure experimentally. So one of these quantities is known as coefficient of thermal expansion, which usually is denoted as alpha. So alpha is defined as coefficient of thermal expansion. Remember what is thermal expansion, as the name suggests. So it is if I increase the temperature, how the material expands. So keeping the pressure constant, I'll measure the change in volume with respect to temperature. So this is nothing but coefficient of thermal expansion. And similarly, the other quantity, which sometimes people write as beta, or sometimes people write as kappa, or sometimes they also write it as kappa suffix t, which is known as compressibility. Now, as the name suggests, that compressibility, so it's basically tells how much you can get a compression for, say, a piece of metal or a gas. So compression means you have to apply pressure and see the change in volume. So it is nothing but derivative of volume with respect to pressure, but you have to define it per unit volume, otherwise you have a problem. So we always define it as 1 over V, keeping the temperature constant. Now if you increase the pressure, you know that the volume will also decrease. So in order to make the parameter constant, we use a negative sign in the definition so that the beta or the kappa becomes positive. Now let us see what is the value of, say, for example, alpha by beta, because that will be useful for our subsequent purpose. Now in order to do that, you see that we have used all these parameters, pressure, volume and temperature, and we can use the cyclic rule for differentiation. If we have, say, 3 parameters, let me write it as the x, y, z way, x, y and z, where x can be written as a function of y and z. Similarly, y can be written as a function of z and x, and similarly for z, which is the case here because I can write the pressure in terms of volume, temperature, volume in terms of pressure and temperature, and so on. So then if I follow a chain of differentiation in a cyclic order, by cyclic order I mean I have to maintain an order, like if I take the derivative of x with respect to y, keeping z fixed, so it is x, y, z, the next one will be y, z, keeping x fixed, and the third one is z, x, and keeping y fixed. So we have to always maintain this order, x, y, z, or y, z, x, or z, x, y. We cannot write x, z, y. So that is a reversal of order. So then it will be -1. So this is known as the cyclic rule in differentiation. So using this cyclic rule, if we take the, instead of x, y, z as pressure, volume, temperature, we can easily get a very nice relation. So I have del P del V T. So I'm writing, say, pressure to volume to temperature. This cycle I'm maintaining. So then the next term will be volume then temperature, keeping pressure constant. The third differential will be temperature, pressure, and volume. That should be equal to -1. Now we have to connect it to alpha and beta. Now remember what is alpha. In the definition of alpha, there will be also 1/volume, because the volume, you have to define it per unit volume. Otherwise, if it will be dependent on the volume of the gas or the substance itself. So we are dividing it per unit volume. In that to maintain that per unit volume, we are dividing it by volume. So alpha is del V del T P. So this quantity is nothing but V into alpha. Similarly, beta is del V del P T. Now this is nothing but 1 over, we can write it as 1 over del P del V T. So this is nothing but 1 over, there is a V missing similarly, so we'll write it as V into beta with a negative sign, and times this del T del P V, that is equal to -1. So what we get, this volume actually gets cancelled. This -1 here will get cancelled here. So all we get is alpha by beta is nothing but, if I take this on the other side, it will be nothing but del P del T V. So you got a very nice relation between alpha and beta, where alpha is the coefficient of thermal expansion and beta is the compressibility, which are measurable quantities, and we can measure the thermal expansion and compressibility for even solids also, not only for gas, but of course for solids the value will be very less, the compressibility value, but still we can get some value. Now we'll be using this relation to get the relationship between Cp minus Cv. Before that, if you remember, so when we are discussing the Cp minus Cv relation, or usually for any many other problems also, we always calculate these two quantities, which we discussed many times. One is del U del Vt. Now already we saw that del U del Vt is nothing but P. If we take the del U del Vt, it will be minus P. So we can use the original notation which we have been using. So it is T into del P del T V minus P. And similarly, we also notice that del H del P T is nothing but, we had minus T into del V del T P, and there will be a plus volume. There is a minus sign, yes. So if you just go back, we just defined the compressibility alpha divided by beta as del P del T V. So this del P del T V is nothing but alpha by beta minus P. Similarly, for del H del Pt, we have, I'll have here a volume term, and then there is a minus T. Now del V del Tp by definition is V times alpha, because alpha is the coefficient of thermal expansion. This is also thermal expansion, you can see, but alpha had it is defined as per unit volume, so there was a divided by volume, and plus V. So we can just organize it a little bit. So we can take the V common, and it will be 1 minus alpha T. So thus we see that we get a very beautiful relation for del U del Vt and del H del Pt, which are 0 for ideal gas, but non-zero for any other system. Any real system, it will have a value. but we are now writing the value in terms of alpha and beta, which are measurable quantities. Now the next thing let us try to do is we can actually write du from the first law as Cp dt plus del u del v t, because I'm just exploring right now where we can utilize these two relation. So du can be now written as very nicely that instead of del u del vt we could use the relation right away, which is t into alpha by beta minus p. Similarly, for the relation for enthalpy dH, we could write for du it will be cv. Cv is associated to always du, and dH is always associated with Cp, and then the next term is del H del Pt, which was discussed many times, and then we can use the second equation for del H del Pt. So it will be Cp dt plus v into 1 minus alpha t. So we basically got two new expression for du and dH. Now what about Cp minus Cv? Now Cp minus Cv we discussed earlier when we discussed the Joule-Thomson effect, and there we got a relation like it will be P plus del u del v t times it was del v del t p. Now what is del u del vt? We just discovered it is this equation. It is t into alpha by beta minus p. And what is del v del tp? Del v del tp is nothing but related to thermal expansion, so it will be alpha times v. We can just simplify this, so the p's get cancelled, so I'll have 1 alpha, and there is 1 alpha, so it will be alpha square v times t minus beta. So what we get is Cp minus Cv is alpha square v t divided by beta. So this is a general relation. Now you can always go back and check with your ideal gas equation. You have to get the value of alpha from ideal gas equation. For example, alpha is nothing but 1 over v is a coefficient of expansion, so it is del v del t p. Now if I use the ideal gas equation, PV equal to n at t, so v will be nothing but n at t divided by p. So the derivative will be nr divided by v. So we can write it down here, 1 over v. So it is nr n at t by v, n at t by p, sorry, and then I'll have p here. So then what I get is PV, and the numerator is nr, so that is 1. Similarly, beta you can easily discover will also be 1. So alpha and beta will be actually equal to 1 excuse me, and since it is actually alpha square, you can see here that we'll have one extra v term that will also cancel, and let us try at home. This is you can try at home that just get the alpha value first and get the beta value, and then explore what is the Cp minus Cv value. And for ideal gas, you should get the Cp minus Cv equal to R. But the point here is that this equation is a very general equation, and you can use it for any other system as well. Now let us summarize what we discussed so far. We discussed the condition for spontaneity and equilibrium, and remember that we had everything is coming from the second law of thermodynamics, where we discussed the ds of the universe must be greater than or equal to 0. if it is a reversible process, the system is at equilibrium, it is equal to 0. If it is greater than 0, then it is a spontaneous process. And then we ultimately ask this question, how the entropy of the system changes for a spontaneous process or a reversible process. Spontaneous processes are by definition irreversible process. Then we got a relationship writing the ds as equal to dq by t if it is reversible, but it will be always greater than dq by t if it is irreversible, if the dq is irreversible. Then we can actually plug in into the first law and then get an equation for du, which we wrote at TdS plus PdV, and then we also TdS minus PdV, and then we also used the same relation to build up other relations. For example, what will be the differential dH, and we also defined two new thermodynamic quantities, A, which is the Helmholtz free energy defined as U minus Ts, and G, which is the Gibbs free energy, which is the G minus H minus Ts, and we got a relation for dA and dG also. Then we just use the method of differentiation, partial derivatives, and to get some differential notation or relations between several thermodynamic quantities, which is pressure, temperature, volume, entropy, etc. And all these relations are known as Maxwell's relations, and we discussed a trick how to remember these Maxwell relations, and we use those Maxwell's relations to get a new expression for pressure and volume in terms of thermodynamic quantities, which we called as thermodynamic equation of state, which is independent of the system. You can plug in your ideal gas equation, you can use your real gas equation and check what are the values. And then we moved on and we discussed what are the values of del U del Vt, which we often discussed, and what is the value of del H del Pt for any thermodynamic system in terms of the coefficient of thermal expansion and compressibility. And then we build up, then we got very nice interesting relations, and then we got a new expression for Cp minus Cv, which is alpha squared Vt by beta. And we'll use these relations in future to solve problems. Now, as a homework problem, what you can try, instead of using the ideal gas equation, you use the real gas equation. You take the van der Waals equation of state, you plug in and you see how these values look like, del U del Vt, del H del Pt, because everything is provided here. So all you have to do is to plug in the van der Waals equation and check how the Cp minus Cv is, what expression you get for Cp minus Cv for an van der Waals equation. Now in the next lecture we'll discuss, we'll start from this, and we'll build on the discussion based on the free energies mostly, because we'll see that what are the, so far we are only discussing the conditions for spontaneity, conditions for equilibrium, what the system is under equilibrium. Now we'll see what are the conditions for spontaneity, how we can connect it to the differentials like du or dh or dg or dA, and which one will be most useful. We'll see that change in Gibbs free energy, which is dg, will be most useful because of some reasons. We'll see that the condition of equilibrium or spontaneity imposes that the pressure and temperature must be constant during the change if we make a change in the Gibbs free energy. And usually for any chemical reaction, chemists also keep the pressure and temperature constant during the change of transformation. So the natural choice is to choose Gibbs free energy. We'll discuss it in the next class. Thank you.